Welcome to the second part of the discussion on fraction, a review of the basic concepts. In the second part, we will start by looking at some questions from the first part that I left behind for you to try. And then after that, we'll continue with the rest of the section. And so let's look at the first section of these problems. We will look at questions relating to operation with fractions. The first question is going to be just simplifying, which is basically adding the two fractions. And based on our discussion, we know that there is a quicker way of adding fractions instead of multiplying by 3 over 3 and on this one here by 8 over 8. We can do this in one step. So question A there, we'll just say this is equal to 3 times 3, which is 9, and 8 times 2, which is 16, and there's a plus, so we'll say plus 16 there, and we divide by the product of the denominators, which is 24. This gives me 25 on 24, which is an improper fraction because the numerator is bigger than the denominator. We can express this as mixed fraction, which is 1 and 1 over 24. I hope you know where that comes from. Okay? The next one there is a difference. So you can see this is a mixed fraction. Before we subtract them, we need to convert this to an improper fraction. And so we can say here 3 and 2 over 5 there becomes 5 times 3, which is 15, plus 2 there is 17. So we can write this as 17 over 5 minus 4 over 5, and as you can see, these are like fractions because the denominators are the same. When they are like fractions, subtracting them or adding them becomes straightforward. So 17 minus 4, which is 13, divided by 5, and that is the answer. It is also an improper fraction. We could convert this to a proper fraction, which becomes, I can write this as 2, because 5 goes into 13 twice, a remainder 3 on 5, like that. Okay, so that's how you solve a question like this. So simplifying, adding or subtracting fraction. You will notice that I've used the terms from the discussion in part 1 of these videos. All right, we'll go to the next question. Okay, so the next question should be still operation with fractions. And simplify. This time we are multiplying two fractions. The first fraction there is a mixed fraction, so we can convert quickly to an improper fraction. 8 times 1 is 8 plus 3 is 11. So we can express this as 11 over 8, and we are multiplying that by 2 on 7. When we are multiplying fractions, it's straightforward. You simply multiply the numerators and multiply the denominator. So 22, 11 times that, and 8 times 7 is 56. And so our answer there is 22 on 56. This is a proper fraction, and we can leave it as it is. Or if you like, we can divide both sides by 2. As a matter of fact, I could have also chosen right here to write this as 11 out of 4 times 2, and then I say times 2 over 7, and this would cancel with that using the unity relation, and that gives me 11 on 28, which is the same as dividing both sides by the top and the bottom by 2 there. And so our answer is 11. This is the lowest form. We've reduced it to the lowest form. So these are equivalent fractions, and reducing to the lowest form, we get 11 on 28. Okay, what about when we have to divide? So the next one requires us to divide. Let me see if I can use a different color here. Okay, and so again, we have a mixed fraction there. I'm going to draw a line here just to give me some kind of space. So 5 times 3 there is 15, plus 2 is 17. So I can write this as 17 over 5. And I am dividing that by 4 on 5. When it comes to division, we know that we can change this to multiplication sign and flip the divisor. This is the divisor fraction. So this becomes 17 on 5 and we multiply by 5 on 4, and we can cancel that and cancel that, and that gives me 17 out of 4, which is an improper fraction, and 4 goes into 17 4 times. Okay, 4 times to give us 16. There is a remainder of 1, so we can write this as 4 and 1 over 4. And this is the result of dividing those two fractions. Okay, so it's that simple. Let's move on. We're answering more questions from the previous section or related to the previous section. Right, here's another question on the same. This should be question number 3. I think I forgot to put a 3 there. And this is now comparing fractions. Says to arrange these fractions in the order or in ascending order. If you check the workbook, we have defined ascending order as increasing order of value, right? So the first question there, we have 3 fractions. The question is which one is the smallest and which one is the largest. So arrange them so that the smallest come first and the largest come last. Now we say there are 2 ways of doing this. In a case like this, we know that we can find the LCM of the 3 denominators, and if you check carefully, the LCM of 3, 10, and 5 is going to be 30. So what happens is we can multiply by 30. We can make the denominator be 30. So the first fraction here is going to be, if we are to make this 30, it means we must multiply the top and the bottom by 10. So then we end up with this one becomes 10 on 30. Okay. The next one, we have to multiply by 3 to have 30 in the denominator. So 3 times 3 is 9, and 10 times 3 is 30. So the denominators are the same. All right. The last one, where we need to make that 30, so we have to multiply by 6. So 2 times 6 is 12, and 5 times 6 is 30. And when the denominators are the same, we refer to them as like fractions. Now we can compare the numerators and see which one is the smallest and which one is the largest. So we know this is the smallest, that's the next, and this is the largest. So if we were asked to arrange them or rearrange in ascending order, we would start by saying 3 out of, so therefore, in ascending order, one moment, and therefore, if we were to write this in ascending order, the smallest is 3 out of 10, followed by a third, 1 over 3, and lastly, we have 2 on 5. So this is the correct arrangement of these fractions in ascending order. If we were asked to arrange them in descending order, then of course means we start with the largest, followed by this, followed by that. Okay, so that's one way of determining which fraction is bigger. And in such a case where it is possible to see the LCM of the denominators, this is the best method to use to find, to be able to arrange the fractions in ascending order, to be able to compare the fractions. All right? Sometimes it's not possible to, sometimes the numbers are mixed, so some of them are given as fractions, some of them are given as decimals. If you wanted to find out which one is bigger, then it would be better to express each of the fraction as a decimal. Then you would be able to tell which one is bigger. So let's see the next question, which we will solve using the second method. Okay, so the next question there is, here we go. So arrange these fractions, okay, not all of them are fraction, arrange them in ascending order. So arrange the numbers here in the order of from smallest to largest. So the best way to do this is to convert, and the reason why we are doing that is because one of them is given as an irrational number. All right, so it would be impossible to try to express that as a fraction. It is irrational, meaning we cannot express this as a fraction. So that means the best way is to try to write these numbers in decimal, maybe to the third or the fourth decimal place. So what is 10 divided by 3? If we divide 10 by 3, you should be able to see that we will get, I think, 3.33 recurring. Okay. Pi is 3.14 1, 5, 9, and so on. All right, so this is to the fifth decimal place, just so that we are sure we can compare with that. And 4/3 is 1.33 recurring, and 22/7 is 3.22. 7 goes in 22 3 times to give us 3. Remainder 1. 7 goes into remainder 1, so 10. 7 goes into 10 ones. Remainder 3, so 7 goes into 30 4 times to give us 28. Remainder 2, 7 goes into 20 2 times to give us 14. Remainder 6, 7 goes into 60 8 times to give us 56, and so on. And once I've written this like this, I can already tell which one is the smallest and which one is the largest. So if we were going to express this in arrange this in ascending order, we can see that this is the smallest, followed by this, followed by that, and then followed by that. So 22/7 is an approximation of pi, but it is not exactly the same, as you can see there. So I will write the smallest number is 4/3. The next number is going to be pi, right? So pi is the next largest number, followed by 22/7, 22/7, and lastly we have 10/3. All right, and we have arranged these four numbers in ascending order. So the second method is appropriate, that is expressing the fractions or the numbers in decimal. This is best if you have some of the numbers appearing as irrational or as decimals. If all of them are fractions, then you want to try, if all the numbers you're dealing with are fractions, if we didn't have that, then it's best to look for the LCM. It becomes much quicker using the LCM to find the largest or to compare the numbers. All right, let's move on to the next question. All right, so these are some of the questions that appeared in the very last few minutes of the first part of the video. The video on fractions. This question requires us to, so we are given an expression like that. In fact, that is an equation, and we are being asked to simplify that equation. Okay, so we said in our discussion that when you have algebraic fractions, so these are called algebraic fractions because they contain unknowns or variables. If we get an algebraic fraction such as this one, then the first thing you want to do is to get rid of the fractional parts, all right? So that you have a linear equation. And to do that, you want to find the LCM of the denominators. So the LCM of the denominators here, we have 4, 3, and 2. The LCM of that should be 12. Easily. So we'll write LCM is 12. If you do not know how to find the LCM quickly, then you can always just multiply all the, the three denominators and you'll get 24. 24 would still work. And so what we want to do now is to multiply each of the three terms by the LCM, which is 12. So I'll write x over 4, right? Plus, so multiplied by 12, and then I'll say plus, I'll say 12 multiplied by x minus 1 over 3, can put that in bracket, and we'll say this must be equal to 12, and into bracket 2x minus 5, everything divide by 2. And the reason why we multiplied by 12 is because now we can cancel easily and say this is going here once, and here it goes 3 times, so that leaves me with 3x there. This goes here once, and here it goes 4 times, and this goes here once, and here it goes 6 times. So that means that cleaning this out, I get 3x, and this becomes 4 times x, which is plus 4x, and 4 times negative 1, which is minus 4, must be equal to 6 times 2x, which is 12x, minus 6 times negative 5, which is negative 30, right? And I can simplify my work here now, and this will give me what? So that's 7x. So I can bring the 7x, this sum here, I can bring it to this side. So I'll have 12x minus 7x on the right hand side, and I can take this to the other side, and I'll have 30 minus 4, and this side will be 26. So 12 minus 7x there will give me 5x. So 5x then must be equal to 26, and so x is 26 over 5, and that is the solution or the answer. I've actually solved two problems at the same time. I could easily have just said 5x is 26. So if somebody says simplify the following equation, then this is the simplified equation. And the next part of the question required us to actually solve it. So once you've simplified the equation like we have done here, so we did that and then simplified it to this form, then now if you're asked to solve the equation where possible, well, yes, we can solve this equation, divide both sides by 5, and we have x is 26 over 5. So that's how you would solve this particular problem. Okay, let's move to the next one. All right, a plus b over 5 minus 2b over 3, and the question is to simplify the following expression. This is not an equation, it's in fact an expression, because there is no equal to something. So the best we can do is really to just add the two fractions. As you can see, these are unlike fractions because the denominators are not the same. So the best way to simplify this is simply to say the numerator, so we're going to have 3 multiplied by that. So this becomes 3 into a plus b, and then we'll say 5 into 2b, and minus, so minus 5 into times 2b, and everything divided by the product of the denominators, which is 15, and that's really what we have. The rest is simply to simplify, so that becomes 3a plus 3b minus 10b, 5 times 2 times b, that is divided by, we divide that by 15. If I simplify this, I get 3a minus positive 3b and negative 10b is negative 7b, everything over 15. And that is the result or the answer we get when we simplify that expression there. So that's not really simplifying an equation, it's actually simplifying an algebraic expression. Okay, that's the way to go about it. We'll look at the next. Okay, says to simplify the following equation. Simplify, and then perhaps, well, again it's saying equation when it should just say an expression, because there is no equal sign of something. So it's wrong to say an equation here. We should be talking about an expression. So simplify the following expression. We have two algebraic fractions being divided, and we've learned that when fractions are being divided, all we have to do is change this to multiplication sign and then flip the divisor. So this fraction here is referred to as the divisor. So therefore we can write this as 3x, 3 into x plus 1, divide by 8, okay, and instead of division sign we'll put a multiplication sign, and then we will have 16 at the top and 5x, 5 into x plus 1 at the bottom, like that. And so when we multiply this, as you can see, this is a multiplication sign, so we can actually cancel. 8 goes here once. I have 8 here, can go into itself once, and 8 goes into 16 twice. And so that leaves me with 2 times 3, which is basically 6 into x plus 1, and in the denominator I have 5 into x plus 1, and you can see the x plus 1 cancels with x plus 1, and I am simply left with, we are left with 6 over 5, which is an improper fraction, and we can reduce that to mixed fraction 1 and 1 over 5, like that. Yes? All right? And so this simplifies to just 6 over 5, or 1 and 1 out of 5. Okay? Let's go to the next one. I think there is probably a part B. Okay, so part B, again, we are being asked to divide those two fractions. All right, so once again, we will write 6pq divided by 5. And instead of the division sign, I can change to multiplication sign and then flip this one, 7 over 12p. And if I look carefully, I can see here that there is a p here that can cancel with a p there, but also 6 goes here once and 6 goes here twice, and that means I can now simplify my expression to 1 times q is q times 7 is 7q divided by 5 times 2 there, which is 10, and that is our result of simplifying this expression. I hope this makes a lot of sense. All right, let's go to, I think, slightly tougher questions. Not tough, but a little more involving. Okay, so here's another one. I think here we only do one of them. I think I've only placed one of the questions. These questions are in the booklet, in the workbook, electronic workbook that I have shared. So simplify, then solve the equation. So this is now an equation because we are saying is equal to 3 or is equal to something else. So when you see an equal sign there, then we can refer to it as an equation. Otherwise, it's merely an expression. So simplify first and then solve the equation. Once again, these are algebraic fractions. I can write 3 as 3 over 1. So I start by saying x minus 2 over 3 plus x plus 1 over 5. And instead of just 3, I'll write 3 over 1, which means the same thing. Now the LCM, the denominators are 3, 5, and 1. The LCM of that is 15. So I can say here that LCM is 15. And so now I can write 15 times x minus 2 over 3 plus, put that in bracket, 15 x plus 1, and this is over 5, and then I will say this is 15 times 3 over 1. Okay, now the reason we are doing this is because now we can say, we can write 3 goes here once and goes here 5 times, 5 goes here once and goes into 15 3 times, and this is just as it is. So I can simplify this. This becomes 5x. So we have 5x minus 10, and we have plus 3x, multiplying 3 by x, and 3 by 1 is plus 3, and this must be equal to 45. All right, rearranging and collecting the like terms together, 5x plus 3x is 8x, must be equal to, so this and this gives me negative 7. Negative 7 goes to the other side of the equal sign, becomes positive 7. Positive 7 plus 45 is 52, and therefore my value, so this is simplifying. First part, we've simplified the expression so that it's just a linear equation like that. And so the solution to this is just dividing both sides by 8, and I have x becoming 52 over 8. That is an improper fraction. I can express that as 8 goes into 52, 6 times to give us 48. So 6 times, remainder 4, and this is 4 out of 8, so 4.5. So this is 1/2. Our value of x is 6 and 1/2. Okay? So the solution to this algebraic equation is 6.5. So the value of x has to be 6.5, like that. Right? So let's, I think we will move on. I didn't place part B, so work with part B, and if you want to show me your results, you're welcome to do so. Otherwise, we can now continue with the rest of the lesson. So let's move on to the last part of this discussion on fractions. And the first part we want to look at is changing numbers from decimal to fraction. I'm actually interested in recurring decimals, but let's see what this is. So a terminating decimal can be expressed as a fraction with a denominator that is a power of 10. So what is a terminating decimal? Any decimal that ends, that has an end to it, is called a terminating decimal. So if I wrote, for example, 0.2, that is a terminating decimal. It's a decimal that has an end to it. Okay? But a decimal such as 0.222, like that, which is usually expressed as 0.2 with a line on top to imply that the 2 continues to infinity, this would be referred to as a recurring decimal. So this is a recurring decimal. Okay? And this here is called a terminating decimal. So a terminating decimal stops somewhere. 0.135 stops at 5. That is a terminating decimal. If it does not end, then it is a recurring decimal. Okay? If you tried to express the square root of 2 as a decimal, it will be 1.412 and so on. It does not end and it does not recur. So it's not repeating itself, but it also does not end. Such a number would be referred to as an irrational number. So this is a non-terminating, non-recurring decimal. This is a terminating decimal. This is a non-terminating but recurring decimal. All right? So I'm interested in a discussion involving these decimals. And so a terminating decimal, any terminating decimal, can be expressed as a fraction with a denominator that is a power of 10. Okay? What do I mean? That is, the denominator can be 10 or 100 or 1,000 and so on. Here are examples. Okay? The number of digits, so just to remember, the number of digits that will fall behind the decimal tells how many zeros belong in the denominator. The number of digits that will fall behind the decimal point on the terminating decimal will tell us the number of zeros that belong in the denominator. And I'm giving you an example here now. All right, so here is one example. So 0.2 has one digit falling behind. So that's the decimal point there. And behind it is just one digit. So that tells me that the number of zeros in the denominator need to be 1. Okay? So I can express this as 2 out of 10. There's just 1 0 because there is one digit behind the decimal point. Similarly, 0.12 has 2 digits behind the decimal point, so I can express 0.12 as 12 out of 100. You can see 2 zeros falling behind, being expressed in the denominator according to that statement there. Okay, so the number of digits behind the decimal will tell us how many zeros belong in the denominator. So in this case, 2 digits behind the decimal, meaning 2 zeros in the denominator. I have one more there. So 0.125, pause the video and think of how to write that as a fraction. So obviously that's going to be 125 divided by 1,000. So 3 zeros in the bottom. Okay? All right, so remember, in such a case, so if you are asked, for example, to express this as a fraction, that is of course the answer, but you would need also to reduce it to the simplest form, to the lowest form, equivalent form. All right, always reduce to the simplest or the lowest equivalent form of the fraction if you're asked to do so. Okay, now we talk about the recurring decimals. We've said a recurring decimal is a decimal number for which the digits are repeated to infinity. Okay, for example, 0.1 with that dash there. So if you see a dash at the top there, it means that it is 0.1 recurring, repeating itself to infinity. Okay. So how do we change a recurring decimal like this? We want to change that recurring decimal back to a fraction. So what we dealt with earlier were terminating decimal. Now I have a recurring decimal, and my job is to turn that into a fraction. So to do so, we want to, if we are going to convert that to a recurring decimal, we will call it R. Let the recurring decimal be represented by letter R, R for recurring. Okay, the next thing is we want to multiply by 10. So a recurring decimal can be expressed as a fraction by subtracting it from a suitable order of 10 multiple of itself. Now that will not make sense to some people, but if I explain it here, it should make a lot of sense. So what we want to do, this is R. So the next thing we want to do is multiply it with a suitable number, order of 10. So 10 or 100 or 1,000 and so on, so that we have the same order of decimal points, the same order of digits behind the decimal point, like this. So if I multiply this by 10, if I multiply R by 10, I'll get 10R equals, and if I multiply this by 10, the decimal point moves forward one step. So this would be 10R. If I express that, I'm going to get 10R is 1 point that. So the important thing is here is that I'll multiply by either 10 or 100 or 1,000 and so on, so that the digits that come behind the decimal point are exactly the same and in the same order as the digits of R. So therefore 10R becomes 1.1111. So you can see behind the decimal point they are all the same. Then the next thing we want to do, so I'll call that my equation 2, and then what I want to do is to subtract them upwards. Okay, so I'm going to take equation 2 and subtract equation number 1. All right? All right. So we'll start with this one, meaning I'll take 10R and subtract R. So what is 10R minus R? We're going to subtract upwards. So 10R minus 1R should be 9R. Okay? And 1.1111 minus 0.1111, this is going to be subtracted from this, and we will be left by just 1. Okay, so this will subtract that, that will subtract that, this one here will subtract that, all this will subtract one another, and we'll have 1 subtract 0, and that gives me on the right hand, I'm going to get 1 on the right hand side. Okay, and that tells me, so 9R must be equal to 1, and that means that R is going to be, if I divide both sides by 9, I'm going to get that R is 1 out of 9, which is telling me, remember we said we let that recurring decimal be represented by letter R, so this is telling me that letter R can also be expressed as 1 over 9, and therefore the recurring decimal 0.1 with that dash on it can be expressed as 1 over 9. This is how we convert a recurring decimal into a fraction. Let's look at another one and see. Example 2. Convert the recurring decimal 0.21 with a dash on it into a fraction. Now you notice that the dash now, that dash at the top, covers both 2 and 1. So that means that the recurring decimal is not just 111, so it's now 212121 like that. So we let R, same thing we did earlier, so we let R represent the recurring decimal. So notice this is 212121 and so on. So this repeats itself to infinity. We want to see what that is as a fraction. Okay? Now, let's see. Can we multiply by 10? So what happens if we multiply this equation by 10 and see if we, the same way we did with the previous one, if we multiply by 10, then we get 2.1 because the decimal point moves forward one step if we are multiplying by 10. Okay? But there's a problem because if we multiply by 10, you can see the digits behind the decimal starts with 2, 1, 2, 1. But the digits behind the decimal here starts with 1, 2, 1, 2, which is something we do not want. We want the order of the decimal, of the digits behind the decimal to be the same. So if this is starting with 2, 1, then we want this also to start with 2, 1. So this here is a problem. Can you see that? So I've highlighted that to indicate that we have a problem here. So multiplying by 10 does not help us to get the same order of digits behind the decimal point. So the better number to use then is to try 100. So if 10 does not work, then we try 100. So I'm going to remove that and try multiplying by 100. So if I multiply this by 100, the decimal point moves forward 2 steps. So it's going to go to 21.2. And now you can see the order of the digits is the same behind the decimal point. So now if we subtract, okay, so the first thing we want to ensure is that the order of the digits is the same in the two equations behind the decimal point. So now if we subtract, so that's my equation 2 now, and now we are going to subtract. We are going to subtract equation 1 from equation 2 there. If we do so, then we are talking of 100R minus 1R, which should be 99R, all right? And on the right-hand side, we're going to have 21.212121 minus 0.2121. So this is subtract or takes care of all that. And on the right-hand side, I'm left with just 21. And now if I make R the subject of the formula, by dividing both sides by 99, I get R is 21 on 99. Which, by the way, I think 3 goes on 21 and goes into 99. So I could reduce that to the lowest equivalent form, and I think it becomes 7 out of 33. I don't know if I've done that. So we get that our answer, yes, 0.21 recurring is 7 out of 33. All right, so I'm hoping you've understood how to convert recurring decimals into fractions. All right. Here are some questions that I want you to try. All right. Convert 0.3 recurring into fraction. Let's do the first one. Or I leave the first one and we do the third one there. So this means, this from here, looking at this, the second one there, we can say that let R be represent as 0 point. Now the line goes through all the 3 of them. So this must be 2, 3, 5, 2, 3, 5, 2, 3, 5, recurring like that. Okay, so the 2, 3, 5 is the recurrence. So if I'm going to have the same order 2, 3, 5 occurring behind the decimal, I need to multiply R by 1000. So I'm going to say here that 1000 R must be equal to 235.235.235.235, like that. Okay, I want the order of the digits behind the decimal point to be the same. So I need to multiply R by 3. So that means the decimal will move 1, 2, 3 steps, and I have 235 like that. And now I have my equation 1 and equation 2. What I want to do now is to subtract upwards, which is to say that 1000 minus R, 1000R minus 1R is 999R, must be equal to, if you subtract upwards, we are left on this side by with 235, like that. And so R becomes 235 divided by 999, and that is the fraction. You can check whether it is possible to reduce that. See if you can divide by 3. I don't see that happening there. And so this becomes our best bet for this fraction. Okay, you can always check by putting this in the calculator and see if you get the same recurring decimal, if you can get this. All right, so that's how you solve that. Now this one here has the dash appearing just on the last 5. Okay, how do you solve that? How do we change that to a fraction? Let's do that one. Okay, so in this case, again, once again, we'll do the same thing we've been doing. Let R, the recurring decimal, be 0.54, and recurrence is on the last digit. So now we can write 5, 5, 5, 5, recurring like that. Okay, now if I multiply by, I'm never going to have 5, 4, 5, 5, 5. It's not possible whatever I do. So in this case, I have to multiply twice. So if I multiply by 100, I want to end up with this 555. So if I multiply by 100, so 100R will give me 54.55 recurring, like that. But that's not enough. Now I multiply this by 1,000, and I say 1,000R will give me 545.5555 recurring. My point is that I want by the two equations I'm going to subtract must have the same order of digits behind the decimal point. So behind the decimal point, I must have the same order of digits. And now I'm going to treat these two as my equation 1 and equation 2. If I subtract upwards, now I have 900R, 1000R minus 100R is 900R, must be equal to 545 minus 54. 545 minus 54, that gives me 1 here, and 14 is 9, and 491, so this is 491, and so my value of R is going to be 491 divided by 900, and that is the fraction. So you want to express this as a fraction, it's going to be equivalent to that. I hope this makes sense, but once again, if you need further clarification, please don't hesitate to ask. We'll go through it together. Obviously, I have placed some questions on recurring decimals in the e-workbook. Please try them out and let's see what you get. Bring them over if you want to confirm your solutions. We will do them. We'll see what you come up with, and we can discuss any question that you find is not working for you. Okay, let's move on. The next thing we want to discuss is complex fractions. Okay, complex fractions. What do we mean by a complex fraction? So complex fractions are also referred to sometimes as multi-level fractions or complex rational expressions. All right? Example of a complex fraction, a rational expression whose numerator or denominator. So a fraction whose numerator or denominator or both contain one or more other fraction or rational expression is called a complex fraction. What am I saying? Here is an example of a complex fraction. So you can see here is a fraction in which the numerator is a fraction in itself. So we have a numerator as a fraction over a denominator like that. That's a complex fraction or a multi-level fraction. Okay, here's another example. All right, so this time the numerator is the fraction. All right, in this case the denominator of the parent fraction, is a fraction. But it can be more complex than that. We can have both numerator and denominator being fractions, such as this one. Okay, or it can also be something like that. So these are examples of complex fractions. How do we deal with complex fractions? At MYP 5 level and above, it's going to be important that you can manipulate this to come up with simplified form of the fraction. All right? Right. So method 1 of simplifying a complex fraction. So if we're going to simplify a complex fraction, the first thing is to ensure that the numerator and the denominator, so let's look at this example, this one for example. The first thing is to combine the two terms in the numerator so that it's just one fraction, and we do the same with the denominator. That's the first step. Okay, and this is method one. The first thing is ensure that you have one fraction in the numerator and one fraction in the denominator. We know how to add fractions, so that's not going to be a big deal. The second thing you want to do is flip the denominator. Once you have just one fraction, we are dividing, so you use the method of flipping the denominator and then simplifying. So perform division by multiplying the numerator by the reciprocal of the denominator. Reciprocal means flipped denominator, as we did before with division, right? And then the rest is just to simplify to get your answer. Let's see how we do that with this particular example. So we want to convert that, we want to simplify that complex fraction. So the first step is to convert that just to one fraction. Okay, so add them so that we have one fraction. So step one there, we're going to end up with that. So that is 5 times x is 5x plus, because this is plus, 3 times 1 is 3, and everything divided by the product of the denominators, which is 15. So we have reduced the numerator into one fraction. We do the same with the denominator. Notice that 1 is basically 1 over 1 there. So if we have that, then x multiplied by 1 is x, and 1 multiplied by 4 is 4. So x plus 4 divided by the product of the denominators, which is just x. That's the first step. The second step is, of course, to take the numerator and multiply by the reciprocal of the denominator. So the denominator flipped like that. So what we have? So we have our numerator there. We are multiplying by the flipped denominator. So if we flip, then x is going to be at the top and x plus 4 is going to be at the bottom, like that. And then the rest of it is simply just to simplify. So we're going to have 5x times x and 3 times x. Okay, so that becomes 5x squared plus 3x in the numerator, and in the denominator we'll have 15 times x, which is 15x. And 15 times 4 is 60, so it's going to be 15x plus 60, like this. Okay, and so we have 5x squared because each of these two terms will multiply x. So x times 5x is 5x squared, and x times 3 is going to be 3x. And then we divide by whatever we get in the denominator, and that is our answer. This is one method of simplifying complex fractions. But sometimes the complex fraction will come in a different form, and so there are faster ways of doing it. So another way of doing this, especially once we have just one fraction at the top and one in the denominator, okay, like that, right? So we now have one fraction in the numerator and one fraction in the denominator. We don't have two of them. So one other thing we can do is to multiply the numerator and the denominator by the LCM of the denominators. So the denominator of the one at the top is x plus 3, and for this one is x minus 2. So we need to look for the LCM of x plus 3 and x minus 2. Once we have that LCM, we'll multiply it at the top and at the bottom. Okay? So method 2, multiply the numerator. So our numerator is the orange one, and the denominator by the LCM of their denominators. Okay? Like this. So the LCM of the denominators of the two fractions is x plus 3 and x minus 2. Basically just multiply them. And then what we need to do now, step 2, is to you can simplify, but then we just need to multiply, right? So once we multiply the top and the bottom by this LCM, we just simplify. Let's see that happen. Okay, step 1, we multiply the top and the bottom by that LCM that we found, x plus 3 into x minus 2, and we do the same at the bottom. Once we've done that, you notice that this is at the top, so it's 5x times that, and you can see this the bottom here, this fraction here, this is at the bottom. So that and that is at the bottom. So you can see this can cancel with that. All right, and similarly, we can see here x minus 2 is here, but it's also there. And that was the whole purpose of doing that. So x plus 3 in the numerator, that one there, cancels with x plus 3 there from the LCM. And we are left with 5x into x minus 2. And in the denominator, x minus 2 and x minus 2 there will also cancel. And we are left with x into x plus 3. So now all we are left to do is to simplify. So I'll have 5x into x minus 2 and x into x plus 3. When we simplify that, you can see x there and the x down there can cancel. And I'm left with 5x minus 10 over x plus 3, like that. And that is the answer or the simplified form of the complex fraction that we were given at the beginning. Okay, I hope that works. Now use this idea to try and answer the questions from the e-workbook. And let's see what you get. Please discuss your solutions. Let's know if you're facing any difficulty. Right, let's try out a question. This is question F. Simplify the following. Here is 1. Please pause the video and try it out. Okay, and let's see what you get. So you can choose to use method 1 or method 2. So of course method 1, let's do it now. I'm assuming you paused the video and you tried it yourself. So let's see if you got the correct answer. So in this case we'll have 10 over 3x, and I will just say multiply by, and I flip that, and I have 6x now at the top and 5 at the bottom. And this goes here once and this goes here twice. 3 goes here once and 3 goes there twice. X is 1 and x there cancels, and I am left with 2 times 2 is 4, and yeah, that's it. So my answer is just 4 for this particular question. Okay, please try the other questions, which I'm just going to show now. Okay, try B there. The first thing you want to do is to combine this into one single fraction, and that is into one single fraction. Please try it out. All right, the next one is also given there, and D is given. Please try to simplify those complex fractions, and let us discuss your solutions when you are done. All right, the last bit of this discussion is on polynomials. What is a polynomial? We're going to use this to discuss polynomial used in rational expressions. So the term polynomial, poly means many and nomial means terms. So this is an expression containing many terms. Okay, for example, if I write 2x squared plus 3x, all right, plus 4. This is a polynomial expression because it has got many terms. In this case, the many are 3 terms. Okay, so an expression that has got many terms such as this one is called a polynomial expression. In fact, this is a quadratic polynomial expression. Okay, and many of you will be familiar with quadratic expressions and quadratic equations. All right, so a polynomial, from the two words poly and nomial, means an expression with many terms. Okay, first of all, let's just look at parts of a polynomial. An expression made of 2 or more terms, each consisting of a coefficient. Okay, so like I wrote there, 2x squared plus 3x plus 1. If I write that, this here is the coefficient. This is the equivalent of the a there. A sub n there is 2 there. This is called the variable, and this is called the power or the exponent. This is the coefficient. So when we say coefficient, this is what we mean there. And x here is the variable. So for the second term, x is a variable, it's just power 1. But here it is x power 2. So the variable is power 2. And this is sometimes referred to as the constant in the polynomial expression. Okay? So where a is any real number, so like 2 there, like 3 there, it can also be 1.5 or a half, whatever. And n is an integer, actually a whole number, which is 0, 1, 2, and so on. Okay? So here this is x. There is an x power 0 here, but we don't write it down. So the powers of x there can be 0, can be 1, can be 2, and so on. Can be any whole number. All right, let me define that now nicely. Okay, example. All right, so my polynomial there started with 2x power 2, like that. So the a, as you can see from here, the a, so this is a term, one term of the polynomial. Like we had 3 terms, this is like one of them, and there will be another one there, and there will be another one after that, and so on. And they can go on to infinity, or they can be 2, or they can be 1, and so on. So that is referred to as a term of the polynomial. The letter a there represents the coefficient of x. All right, and x itself is called the variable. Okay, and the power there, the n, is the power or the exponent or the degree of the polynomial or the order of the polynomial. So there are three words that we can use here. We can say this is the order of the polynomial, or the order of that term, or the degree of that term, or the power. Okay, so that is a polynomial. Here are some examples of polynomial. Okay, so we will write a polynomial here, and we'll talk about what the degree is, and we will class them by their degree as well as class them by the number of terms they have. So 5 technically is not a polynomial by itself, because we need at least an x power 1. This is 5x power 0. It is just one term. So if it was a degree, we would say degree 0. All right, and class by degree, we refer to this as a constant. And class by the number of terms, because it has got one term, we will say it is a monomial. Okay, a monomial polynomial. Monomial is if there is only one term in the polynomial. Then we have 3x. Again, you can see that's just one term. So that will also be a monomial. Okay, the degree of the polynomial is 1 because the highest power there is 1. Okay, so we say degree 1 or first order polynomial. Okay, class by degree, we refer to that as a linear polynomial because it has got the highest power there is 1. So if the highest power of x is 1, then we'll refer to it as a linear polynomial, or polynomial of first order or first degree. All right, since it is only one term, with that polynomial there is also a monomial. Okay, the next one there has got 2 terms, and therefore we would refer to it as a binomial polynomial. Binomial meaning having 2. Okay, once again, the highest power of x there is 1, so this is a first order polynomial. And because the degree is 1, that is the first order, we refer to it as a linear polynomial, like a linear equation or a linear function or a linear expression. Okay, y is mx plus c is the equation of a straight line. It's a linear equation. Okay, because there are 2 terms, we've said this is called a binomial polynomial. Okay, a binomial expression. Here's another one. So 5x squared plus x. This is a polynomial with 2 terms. Okay, so the degree is the highest power of x, so this is a second order polynomial, or a polynomial of degree 2. So second order polynomial. And class by degree, because the highest power of the variable is 2, this is called a quadratic polynomial. So it is quadratic, and because there are 2 terms, it is a binomial polynomial. All right. Lastly, this one has got 3 terms. The highest power there is 3, and so we call this as a third order polynomial or a polynomial of degree 3, okay? Because the highest power is 3, we refer to this as a cubic polynomial, okay? So class by degree is called a cubic polynomial, and because we have 3 terms there, it's not binomial. Binomial means 2, so it's going to be called a trinomial polynomial. So these are just some terms we use to when we are referring to polynomials, okay? All right. Next, we want to see how to divide polynomials. So if I have a polynomial, we want to divide it by a monomial or a binomial or a trinomial. Right. So divide each term in the poly. So we want to divide by a monomial here. So if we are dividing by a monomial, if we have a polynomial and we want to divide it by a monomial, we divide each term in the polynomial by the monomial. Okay? Like this. So assuming this is a polynomial expression and we are dividing by a monomial. So this is binomial. We are dividing by a monomial. Then all you want to do is to divide each of the terms of the numerator by the monomial in the denominator. So therefore A divided by C plus B divided by C, like that. So that is the rule that we use when we want to simplify. Okay, let's look at an example of this. Dividing a polynomial by a monomial. Here is a polynomial. A rational expression is a quotient of polynomials. So when we talk of a rational, like what we just looked at earlier, that would be a rational expression. The numerator will be a polynomial, the denominator will be a polynomial. So rational expressions are division or quotients of polynomials. So the top and the numerator and the denominators are polynomials. Like this. Okay, so here is an expression, a rational expression, in which the numerator is a cubic polynomial, okay, with 3 terms, and the denominator is a monomial, okay, a first order monomial, and that is a third order polynomial. So if we wanted to divide this, if we want to simplify this expression, we have said divide each term of the numerator by the monomial in the denominator. So this is how we divide by a monomial. What am I saying? So we are going to have 6x power 3 divided by 2x, then minus, okay, 12x squared divided by 2x, and then plus 10x over 2x. And then the rest is simply to simplify that. If we simplify this, we should get 3x squared. I hope you can see that because we have 6 times x times x times x, and then we have 2 times x. 2 divides that, we get 3. X cancels one of the x's and we are left with x squared. So we can express this as 3x for the first term there. The second term is going to be 6x. I hope you can see that. So minus 6x. And the third term is going to be 5 because x cancels with x, and 2 goes into 10 5 times. So this is 5. And so we write that. So we have simplified that expression by dividing each term by the denominator there, and this is the reduced form of that expression. Okay, that's how we divide a polynomial with a monomial. Okay, what about dividing by a binomial? Now this is a little bit more, requires a number of steps, but we are going to do it. I hope at the end of the day you know how to do this. Okay, anytime you are confused, you come back and look at, watch the video to remind yourself of how we did this. So here is an example of a cubic polynomial with 4 terms, and we are dividing that by using a binomial polynomial in the denominator. Okay, so how do we divide this? Now we can no longer divide each term by this just directly like that. So we are going to use the method that we use with the regular numbers. So if somebody says divide, what is 253 divided by, let's say, 4? Okay, what do we normally do? Well, hopefully you have learned to do this. 4 out, 253 in, and then we say 4 does not go into 2, but 4 goes into 25 6 times, So we write 6 times there. 6 times 4 is 24. Then we subtract, we get 1 as a remainder, and we bring the 3 down. We have 13, and we say now 4 goes into 13 how many times? And we can say 3 times, and 3 times 4 gives me 12, and so subtract, and we have a remainder of 1. So here we are subtracting like that, subtract like that, and we have a remainder of 1. And because of that, we will say that 253 over 4 can be expressed as 63 and 1 over 4. Okay, so we've learned how to divide that. Hopefully we all know how to do this. We are going to use this same method to divide that. Okay, let's see how we go about it. Okay, so the first thing we want to do is to arrange them the way we arranged our numbers there. So x minus 2 outside, like that, and then we are going to divide by that. So how do we go about this? We start by saying, so this, just a slight difference, but basically the same process. So going forward, we consider just the x, and we ask ourselves, so we'll take x and divide by each of the terms accordingly in steps, okay? So we'll say x goes into x power 3 how many times? In other words, what do I multiply by x to get x power 3? And the answer is x squared. So I'm going to write that x squared up there. All right, so we have x squared up there. So we are saying x goes into x cubed, x squared times. All right, so I need x squared to multiply by this to get x cubed. Now I multiply back like we did before. So x squared multiplied by x will give me x cubed, and x squared multiplied by minus 2 will give me minus 2x squared. And then what I'm going to do, just like before, draw a line and subtract. So we are going to subtract the two parts. So x power 3 minus x power 3 disappears, that's 0. But negative 8x squared minus negative 2x squared is actually minus 8x squared plus 2x squared, which gives me negative 6x squared. Okay, and once I've done subtracted, then I bring these ones down. So I'm going to bring this down. So I bring that down, okay, and then I repeat the process. X goes into negative 6x squared. In other words, what do I need to multiply by x to get negative 6x squared? Well, the answer is negative 6x. So I write my negative 6x up there, okay, and then I multiply back. So negative 6x times x there will give me negative 6x squared, and negative 6x multiplied by negative 2 is going to give me positive 12x. Once again, I subtract, just like before, right? We're going to subtract. Negative 6x squared minus negative 6x squared is 0, but 9x minus 12x is going to give me negative 3x. All right? Now I bring my positive 6 down. If I bring my positive 6 down, and then I repeat. X, what do I multiply by x to get me negative 3x? Well, I need negative 3, so I put negative 3 up there, and then multiply back. Okay, so negative 3 multiplied by x is negative 3x, and negative 3 multiplied by negative 6 is positive 6. Okay, draw a line and subtract, just like before. Now if I subtract this minus that is going to be 0, and 6 minus 6 is going to be 0, so this is going to give me 0, so there is no remainder, and therefore this expression divided by that is just going to give me this expression here. So my answer is actually what you see there, and so we can conclude that this division here gives me, if I divide x cubed minus 8x squared plus 9x plus 6, if I divide that by x minus 2, I'm going to get x squared minus 6x minus 3. I want you to, just watch the video again, go back and check what we've just done there, and be sure that you can answer these questions, all right? Sometimes there will be a remainder. Okay, sometimes when you subtract, you have a remainder there. So you'll have your answer here, and then you say plus the remainder over x minus 2. Okay? All right. What I want you to do is to try these questions. Use the long division to simplify this. So what we've just done there is called algebraic long division. Okay? Use the algebraic long division method to simplify the following. So I want you to find the solution to that. And that, and that. So try to divide those and come up with a solution. I'm showing you the solutions shortly, but you can pause and try and divide those three, solve those three questions. And here are the answers. Once you are done, check if you are getting these answers for the three questions. So the first one should give you a value of that. The second one should give you that there is a remainder of 1 out of the divisor. And the third one also gives you an expression. This is what goes up there. And there is a remainder of 2 out of the divisor, like that. So please check if you're getting these same answers. And let's discuss your solutions. If you're facing difficulties, let me know. And we can go through them together. Okay? Right. And this brings us to the end of this discussion on fractions. I hope that you're able to understand this. Once again, if this has not worked very well for you, let me know and I can give further explanations. With this lesson now done, you should be able to answer all the questions that appear on the workbook, on the electronic workbook that I've shared with you. If you face any difficulties at all, please ensure to contact me, send me a message, and we'll go through it together. If you found this video useful, please consider subscribing and liking the video. This way, when we produce new material, you will be notified. But also consider sharing the video with others who might also find it useful. Okay? Students in MYP4, a lot of students, many students find this work difficult. Students in MYP4, sometimes, some of them will not be able to do polynomial long division. But hopefully by watching the video, they will be able to try it. So do share the video with them. And I will see you for the next subunit. All right? Thank you and bye.